is too far.
Not quite. Should resist too many anecdotes, probably. That's usually how I
But let's maybe start now. It's my pleasure to introduce Ted Shepherd, who is here from the University of Reading, where he's based in the meteorology department and is the Grantham Chair of Climate Science here. Over to you, Ted.
Okay, well, thanks, Antje. So my title is probably a bit aspirational, and I was thinking that I was a postdoc in Cambridge with Michael McIntyre, and I think he would put on front of every single title. So it should really be called On Bringing Physical Reasoning, but some journals don't like that word. It's some thoughts in this respect, and they're probably going to be very naive from your point of view. And I guess it's a bit of a dialogue to start trying to combine statistical practice and physical reasoning. I don't really work much on the S2S time scales. I more work on the climate time scales, but I've been getting into this area, so it's some thoughts. So I guess the first thing to start with is forecasts are ultimately to inform decisions, right? It's not just for our interest. People make decisions based on forecasts, and forecasts are uncertain. And people say, well, we just need probabilistic forecasts, but it's not quite so simple because it depends on the uncertainties. And this is from an essay by Andy Sterling in Nature. It's not about weather or climate. It's much more general. And he had this uncertainty matrix where he classified the two axes are the knowledge about the possibilities, unproblematic or problematic, and are the knowledge about the probabilities, unproblematic or problematic. So in the upper right corner, you have what's called risk. This is the Knightian, Frank Knight, the economist. It's risk as meaning quantifiable uncertainty. It's not the way that the term is always used, of course, but classically that would be Knightian risk. And in this case, if you're confident that you know the possibilities and you're confident that you know the probabilities, then you can try to do risk assessment and optimization and so on. But as the knowledge about the possibilities or the probabilities become more problematic, then you move down to the lower or the left or the right or the lower quadrant of this matrix. And of course, there are many situations that are like that, and there are methods that deal with those things. But he makes the point that scientists are under often political pressure, but it could be pressure from journals that want a very single definitive headline or all sorts of things that try to push us into the upper left corner where we issue single definitive statements. And I think more on the climate side, for me, this, for example, in consensus mode, IPCC issues single definitive statements. So what that leads to is reliable but rather uninformative statements. So, for example, the summary for policymakers of the last IPCC Working One report, if you want to know what's going to happen in the North Atlantic storm tracks, which is very important in this part of the world, they'll just say that there's low confidence in the changes. Okay, that's true, but it doesn't get you very far. They could have done it differently. So I think we need a language for expressing a plural conditional state of knowledge. These are the terms that Sterling used. And I think that's also true on the S2S timescales because the uncertainties get much bigger than what we're used to on the shorter term timescales. Of course, I'm thinking of large scale dynamics. And what that means is multiple mutually exclusive hypotheses and a logic for structured scientific reasoning. And now you'll all know that points us towards Bayes, but I'm not certain. But I'm going to push a kind of a soft form of Bayes. But the statistical practice, I think, in the mainstream, not in data assimilation and not in certain particular fields like pollution, source inversion, and stuff like that. But in general, it's frequentist. We just count ensemble members. And frequentist statistics has no language for this, no language for multiple mutually exclusive hypotheses or any logic behind it. So that's our challenge. And of course, as you probably know, there's been a lot of arguments against getting rid of the concept of statistical significance. This is an editorial from Nature three and a half years ago. It's ignored by all the Nature editors, and reviewers, but it's at the high level. And this, of course, is across many areas of science. The point they make, the main point that they're making here, and this was signed by 300 statisticians or something, is that a p-value of 0.05, less than 0.05, which is a standard level, should not be interpreted as true or false. But the issue runs much deeper than this, and I've tried to talk about this in an essay that I published in Climatic Change 6 months, well, a year ago almost now. So you refer you to that. It's about climate science, and in climate change science, and I think S2S prediction will be the same. It's anchored in physical understanding. We always think about mechanisms, yet frequentist practices, which are essentially rituals, absolutely dominate published climate change science. And I can give you lots and lots of ideas about this, but they're absolutely leading lights in the whole field. It's not just people that aren't trained, it's the most famous scientists in the world, including IPCC for that matter. This creates a disconnect between the physical reasoning and statistical practice. And Guy Grenzer, who's a psychologist, who's published a lot of popular books, has this paper I really like from 2004 called Mindless Statistics. He talks about the null ritual of setting up a null hypothesis, but don't specify your own hypothesis or any alternative hypothesis. Use the 5% significance level for rejecting the null and accepting your hypothesis, and always do it. Now, he's talking about social sciences, but I think it's exactly the same in climate science, and I have many, many, many examples, as I said, in top journals by very famous scientists, which I won't show you. Just to give an example of why we might be worried about uncertainty, I co-lead a WCRP Lighthouse activity called My Climate Risk with Regina Rodriguez, who's an oceanographer in Brazil, and we published a perspective in PNAS Nexus earlier this year, in which we included a case study of this compound event in Brazil when in 2013-2014 the monsoon circulation failed. And so that, in general, the climatological precipitation, there's this South Atlantic convergence zone, and the moisture flows off the Amazon. The Amazon is actually a source of moisture, but there was a blocking anticyclone, which blocked the moisture flow, also led to clear skies. So you had the combination of lack of precipitation and a lot of very hot conditions over land as well as ocean. And it basically created, low water levels in the reservoirs for hydroelectricity, agricultural drought, heat waves affecting fisheries, and so on. So it was one of these classic examples of correlated risk across the food, energy, water nexus. So there's a practice called a probabilistic attribution or rapid attribution. It's semi-rapid attribution. And they look at the different probabilities. They create an event class, univariate typically, and they look at the risk ratios. So this was published in the special issue of BAMS a number of years ago, and they had a drought risk ratio. So greater than 1, this is a log scale, means that climate change increased the risk of drought. Less than 1 said it decreased. The observations show a tendency towards increase, and the CMA 5 models for what they're worth show a tendency towards increase. The 2 versions of the Met Office model that they looked at showed a decrease. They pooled the error bars, which of course you shouldn't do. There's no logical basis for following the rule of errors when you've got systematic errors, and they couldn't reject the null hypothesis. So they said there's insufficient evidence that climate change increased drought risk. But you can ask insufficient for whom? If you were a water manager and so on, especially given the observational trends, you would probably think more carefully about this. So you all know Bayes' theorem here, of course, and so I just show Bayes' theorem in the odds form, which I think is convenient. And so if we think of H as being a hypothesis, of course the null hypothesis is a classic one, and then not H, the negation of H. So the p-value is the probability of the data given the hypothesis, but to interpret it, you need a well-defined alternative hypothesis. It's just clear from Bayes' theorem. You simply can't derive anything from a p-value without considering an alternative hypothesis, more of a one that you can define and you can calculate a likelihood function. And that gives you a Bayes factor. You can't just go fishing with vaguely specified alternative hypotheses. This happens, at least in climate science, all the time. And And I think even in this S2S, at least the seasonal context, a little bit, I would say as well. I mean, you can also see that you need prior odds on the right. If you don't include that, you're throwing out all the background information you have. Of course, as you know, I guess if the prior odds are even, then you can just look at the base factor, which gives you the posterior odds. But you know, nowhere in any climate science publication, now I don't read data assimilation papers, but nowhere in any climate science publication have I ever seen a discussion of the probability of the likelihood function of the alternative hypothesis or base factor or prior probabilities, just p-values, just absolutely crazy. Now, causality is another point. It, of course, doesn't come up if you look at most statistics textbooks, at least the classic ones like Wilkes or von Storch and Zwiers, you won't find that word anywhere. As you know, there's been much growing interest in causality, and one of the gurus is Judea Pearl. This is this popular book, co-authored with Mackenzie, on the book of why. He's got more technical books as well. And I think it's clear that understanding causality is crucial for setting up the statistical analysis and interpreting the results. If you look at any paper, any publication in weather and climate science, there's always a causal framing. It's just generally in words. And the point is that the mathematics is agnostic about causality, but the physical interpretation is not. If you had enough data and the problem was that statistically stationary, then maybe you don't have to worry about causality. But we're interested in non-stationary problems. We're interested in out-of-sample problems. We're interested in counterfactual questions. For all of those things, you need causality. And just to give a simple example, this very basic three variable setup, you have a variable y, which you know is influenced by both x and z. You happen to know that x and z are correlated. I don't point an arrow here. And then if you just so this is in the linear case, if you just regress y against these two variables x and z, you get the first. This is an MLR. And then if you look at the correlation between y and x, you see that there's two terms. One is essentially a direct pathway. So the correlation reflects a combination of a direct pathway from x to y and an indirect pathway, which is via z. And this is a special case of what's known as the path tracing rule, and it's of course it generalizes to nonlinear setups. Marlene Kretschmer led a paper that we published in BAMS that's really pedagogical on applying this to different teleconnections, just to try to get these concepts out there in the climate literature. So an example, so the southern hemisphere mid-latitude jet here, we might look at the NAO or something, but in the southern hemisphere, you look at the jet latitude, sometimes known as the southern annular mode, but you can look at the jet latitude. And in the early austral summer, it's correlated with El Nino, and the correlation is about is minus 0.14. But it's also known that the southern hemisphere mid-latitude jet is affected by interannual variability in the seasonal breakdown of the stratospheric polar vortex, and we'll say more about that later. So if you do a multiple linear regression, you actually find that the direct linkage is rather small, minus 0.04, and the one from the vortex is 0.39. But there's a correlation between ENSO and vortex. And now I've drawn an arrow because there's no theory or any proposition that El Nino is controlled by the state of or affected by the state of the stratospheric polar vortex, but there's lots and lots of evidence that the vortex is affected by ENSO because it generates planetary Rossby waves. So in this case, you can draw the arrow here. I forgot to mention that in this case, you can see that if the arrow runs from x to z, then z is a mediator, which is the case I'm just talking about. But if it ran the other way, then you would regard z as a confounder. And obviously, your interpretation is very different depending on whether it's a confounder or a mediator. And so you see, in this case, the correlation is coming about 1/3 from the direct pathway of ENSO and about 2/3 from the vortex through the vortex, and you can see that it all adds up. The nice thing about this is very simple, of course, and you can generalize to more complex causal networks where the rules become much more complicated, but they follow axiomatic principles. The nice thing about multiple linear regression is that it provides a built-in narrative. So we often have a narrative after the fact, but this is part of the analysis. It isn't arbitrary. It's essentially the physical interpretation is basically wedded to this statistical analysis. As I say, it generalizes to conditional probabilities that don't have to be linear, and you can use it to construct storylines of conditional explanations for complex events, which is another talk on its own, which I won't go into. So I'm going to give two examples of recent things that I've been involved with. Both are from MPE, CDT, PhD students. I've been fortunate to have three, actually. Adrian's here, Swinda Volcana, and Elena Sajuro will be graduating soon. So this first is from Swinda's work, and Andrew here is a co-supervisor along with Jan de Wils from Potsdam. So you may know that in the, this is to do with North Atlantic wintertime circulation regimes. You may know that the circulation regimes, these are shown in terms of the 500 hectopascal geopotential height anomaly. They're widely used as a diagnostic of the slowly evolving aspects of weather conditions. So we have day-to-day weather, but then we have regimes that are evolving on a more like a 10 to 14 day timescale or so quite relevant for S2S. There's still a lot of debate about whether these regimes are somehow, nonlinear or not, but you can just look at it statistically, and different groups have different numbers of regimes. 4 is the classical number. The Karlsruhe group has 7. We came up with 6. Probably doesn't really matter in most cases. So you see that there's the North Atlantic oscillation, which is the classic regime. We split into plus and minus, not just a linear mode, but there's also the Atlantic Ridge and the Scandinavian blocking, and they're opposite. They're not the opposite phases because they're not exactly opposite, but you can see that they're broadly opposite. So in the standard methodology here, which is very, very widely used as k-means clustering, this of course has day-to-day variability. So you want to filter that somehow. And what's being generally done in the literature is to use either spatial or temporal filtering. But we're trying to follow the approach of using full field data and don't pre-filter, but do the filtering as part of the analysis itself. So it was a form of regularization within the procedure itself. Now, just to, I think Angela mentioned the signal-to-noise problem this morning. I say there are claims because sometimes they don't quite stand up, I think, but I think in the NEO it's clear. But that atmospheric circulation has less predictability in models than it does in the real atmosphere. So it's being called the signal-to-noise problem or the paradox or deficit or something. Now, it's usually quantified through the anomaly correlation coefficient or things derived from that. There's also this the other metric that I forget about. But the ACC is also a measure of the noise. And if you're really interested in the signal, because how well can we estimate the noise? If you're really interested in the signal, then regression seems the more obvious approach. So we used regression here, regressing the observed variability. This is for the wintertime average of the different regimes versus the prediction, the ensemble mean. So it's the way which should be capturing the signal. The hypothesis is that the ensemble mean will capture the predictable signal. And so just to show the NEO index, you see that the regression coefficient is about 2, which is roughly what other groups have found. This is for the ECWF system 5, but a factor 2 deficit seems like quite a common number. But if you look at the NEO plus, you see that it's about 1. And actually, the negative of the Scandinavian blocking is also about 1. Those are the zonal regimes. So it seems that the zonal regimes don't have any signal noise problem. The NEO minus has 1, but it's not really there's no real a signal here. You can see that the p-value is quite large and the base factor is close to 1. So there's no predictability there. So the problem clearly lies in the lack of predictability of the NEO minus, which is the blocked regime, which we obviously would be an interesting avenue to explore. But I think it also, as a general theme, shows the perils of aggregation, because we tend to aggregate a lot. You have to aggregate if you're going to do statistics, but aggregating NEO plus and NEO minus actually isn't helpful because there is a signal which is predictable in NAO plus and there isn't in minus. So treating it just as an NAO index is actually making it much more complicated to understand what the problem is. So I think that's one of the lessons here. Now, k-means clustering is categorical. You're either in a cluster or you're not, but the regime assignment should arguably be probabilistic because of the noise. So these were just the distance. These are the distributions of the distances from the different cluster centers for different regime assignments. So, for example, in the NAO, this is showing for states which are classified as NAO plus. This shows the distribution of distances to NAO plus itself, which is of course a small number, or the other ones. NAO minus is actually large, but so you can see that they follow distributions are actually pretty close to normal because we're a long way from zero here because of the noise. So you can compute a likelihood function. You can just say what's the likelihood of that state being in a certain cluster, which means you can use Bayes' theorem. So we've used Bayes' theorem as an alternative to regularization. And most of the predictability, it's a very simple application of Bayes' theorem, really, I think. And most of the variability is actually coming from El Nino. And you can see that in the satellite record of almost 40 years, there's 3 El Ninos and 5 La Ninas. So it's a pretty small sample size, but the peaks and troughs really line up. So you have confidence that it's something real. And I think, again, you have to treat La Nina separately from El Nino. If you just used an ENSO index and an NAO index, you would lose a lot of this. So I think there's some potential to try to bring some of these methods in, which can be still connected to the way that people are actually doing things in practice. One of the points is that if you try to, it's been argued that to deal with the signal to noise problem, you really need large ensemble sizes of 50 or more. That's quite costly, of course. Turns out if you just focus on the ENSO signal and the regimes, even with 10-member ensembles, you can get a lot further. So I think there's potential to try to use some of these methods to avoid having to use massive ensemble sizes, because that really is a limitation in the different options. So finally, and I realize I'm getting close to the end here, I'll mention Elena's work, which is on the southern hemisphere coupling. I've already said that the stratospheric vortex affects the troposphere through this coupling mechanism through planetary waves. And this is from a former student, Nick Byrne, who was not in the CET. This is the difference in the zonal mean zonal wind between what you would classify as strong and weak vortex states. And you can see this is pressure altitude here. For those of you who aren't used to stratospheric pressures, one is about 50 kilometers. So the top half is more or less stratosphere, and the bottom half, or bottom third anyway, is troposphere. And you can see that through the seasonal cycle, there's this propagation downwards, and it's especially strong in the troposphere in this spring to summer transition period, which affects the jet stream, as I've already talked about. So first thing Ellen did, this was just using observations, was to use a very simple statistical model. It's a causal model, but it's really trivial. You just have autocorrelation of the stratospheric vortex and a single lagged causal link from the vortex to the tropospheric jet. Now the interesting thing is that if you look at this is in 35-day blocks. If you look in the correlation structure, these are in units of 35 days. So the top left, these are small labels, is the autocorrelation of the polar vortex. And you can see that this is lag 1, 2, 3, 4. And the red is the observations, and the blue is a prediction from this very simple model with only 2 numbers in it. And you predict the autocorrelation of the polar vortex. There's an autocorrelation of the jet. There is no autocorrelation in the statistical model. It's coming entirely from the autocorrelation of the stratospheric vortex and the downward propagation. And then you can see correlations where the jet is a predictor of the polar vortex, or the polar vortex is a predictor of the jet. They look pretty similar, actually, but the causality in the statistical model is purely downward. There's no upward causality built in. So it just shows that correlations, of course, are extremely dangerous to interpret naively. You need a causal model to help interpret them. And just to illustrate the non-stationary point, she used this model to predict how the ozone hole would affect the tropospheric jet in the period where the ozone hole was building and where it was decaying, and it seems to work. So you can apply a non-causal forcing as long as the link is stationary. So what she's finally doing for the last part of her thesis, which is not quite finished, is develop a Bayesian causal network model to try to show the different causal factors. This is all from literature. Every link here is discussed somewhere in literature. I won't define all of these terms, but it's basically altitude in the y-axis and month in the x-axis. And you can see the strongest links are in the dark lines here. The kind of thing that you can do with this, because it's a Bayesian model, now you can say, what would it take to give me an equatorward shifted eddy-driven jet? 2 is the eddy-driven jet in this spring, in this late spring or early summer period, or a poleward shifted jet, and you can see the effect that these two states have on ENSO or the PGO or various drivers. So it's an interesting, as you know, Bayes' theorem allows you to work backwards, and then you can say, what would it take to create this kind of event, and think of early warning systems and so on. So that's all I want to show. I'm sorry it's been rather quick, but just to say that the scientific reasoning in climate science, and I think it applies to S2S as well. Of course, we have model biases and all these things as well. It's a combination of physically based logic and statistical calculation, and I'm a big fan of Harold Jeffrey's book on probability. Third edition was 1961. First edition, I think, was 39. He said it's sometimes considered a paradox that the answer depends not only on the observations but on the question. It should be a platitude. Most, although not all, climate science is still dominated by frequent statistical practices, and inferences tend to be treated as true-false statements. Does the Arctic affect mid-latitudes or not? True or false? It's always presented as true-false. The divorcing of physical reasoning from, or causal reasoning from statistical practice goes back in history. I think Laplace combined them, but then in the late 19th century and especially early in the 20th century, UCL, I think, bears a lot of responsibility for this, has divorced physical reasoning from statistical practice. And I think it has to be, statistical practice has to be embedded within structured logical reasoning, for example, in the form of causal networks. I'm not necessarily arguing for a full-blown Bayesian analysis. It may have its purpose in particular problems, but in my experience, it can quickly become opaque. And if you want to connect to decision-making, the methods have to be transparent and interpretable. But I am arguing for some of the following the very basic logical principles of reasoning under uncertainty. Thanks so much.
We now have time for questions.
Oh yeah, sorry.
There's one in the back there.
But then you didn't have to bring the light back.
Hello. So you're thinking of nice talks. Fairly early on, you had a slide about the p-values and the fact that people don't take into account these factors in Bayes' theorem. So, unless maybe I haven't understood fully, but I mean, I thought in some sense the whole point of statistical hypothesis testing and the p-values and so on is that you're presupposing that you don't have the ability to address any of those other objects. So now if you did, then we're not sure you'd bother with p-values. You just say, here is my condition, my Poison's theory of distribution. But I guess the whole point of a p-value is you say, well, okay, I have my null hypothesis. What's the problem?
Yeah.
I don't know how to try any underlying probabilities except those given by the null hypothesis. Now, how extreme is my result?
Yeah. I guess we need the mic back to wait for it. If I'm going to be audible. Or does this pick it up?
This is also
Oh, okay, very good, sorry. Yeah, that's a very good point, and I guess that's one of the criticisms which I think is made by Gigerenzer actually, is that this null hypothesis, a significance test, is sort of a bastardization of two different things. One is the classic p-value, which is when you don't know anything and you haven't looked at the data. But in climate science, we have always looked at the data, and we have lots of ideas. And so people are not using, so it's a critique not of the p-value, but of the null hypothesis test, right? I think that's the point. So what you say is absolutely true, but it's not the way it's used. And in climate science, it's used as a proof. It should be used, apparently, according to Fisher, as the very first step that you would do. It's exploratory, just to ask. I mean, it is reasonable to ask, is what I'm seeing due to chance, or is there maybe something there? So if it's the first step, that's right, but that's not the way it's used. It's used as the final step. And I can show you lots and lots of examples in climate science. So I think, no, there's nothing wrong with the p-value. Actually, it's part of the Bayes factor, after all. So I guess you're saying that it could be a first step. But then if you're gonna, as I said, in that quote from Gigerenzer, people do have an alternative hypothesis. They just don't specify it. So they're cheating.
Is that sometimes also the problem with attribution, that there's no alternative hypothesis?
Extreme event attribution. Yeah, okay. I think that's. I think there's partly I think one of the problems is that you're treating epistemic uncertainty as aleatoric uncertainty. So you pool all these uncertainties. Now, no measurement scientist would ever combine random error with systematic error. People spend huge efforts to try to separate these things, but somehow in climate science, we just throw it all in one bin. So that's one thing. So, and that's where the storyline thing comes in, actually, because I think you would have different, for example, in the Brazil case, there are different theories for how climate change, or hypotheses, I guess I could call them, for how climate change might evolve in terms of the monsoon circulation in that region, and you could construct hypotheses, we call them storylines, which are physically self-consistent possibilities, but they're just hypotheses, really, and you could then test the different hypotheses using Bayes factors and decide if there's enough weight to go. It would depend on your decision, obviously. And the same thing could be used in a forecasting context, right? So you could construct storylines of different forecasts that might be of concern for different sectors and compute Bayes factors. And I think it's all very doable, because we should be able to construct p-values or likelihood functions, I think, for these alternatives, but it's not what has been done.
Any more questions?
So maybe just a very specific one, that you have this one example in the ICCP report, which was based on consensus, something about the North American.
Oh yes, yeah.
Atlantic, I can't remember, it was very early on. What would you suggest that they should have done following?
I don't think IPC, one of the problems, or I shouldn't say problem, one of the constraints, well, there's a couple of constraints on IPCC. One thing is that the summary for policymakers has to go through a line-by-line review, which is a huge effort. They argue over every comma. And so the scientists have to write statements that are absolutely bulletproof. They would never try to put something in which was at all tricky, because it will never pass that. So that's a very political thing, that you just know that you're going to have to defend every single phrase. And so they're very conservative. Now, you can put other things in the technical summary or the chapters which don't go through that process. They still go through peer review, but it's not this excruciating line-by-line thing. But of course, IPCC has to serve the whole world. There is still going to be review, there is a peer review process, and I don't think it's not an established practice. So I think they would have trouble. They have put their toe in the water with storylines, and they've talked about it as a possibility. And I guess in chapter 10, they did it through case studies. So which is not they're sort of just testing the waters. So Cape Town drought and some other, there were cases where they articulate several hypotheses. They didn't actually do anything they didn't make it quantitative. But I think there's beginning to be a movement, but you need a pretty strong literature base for it, and then the reviewers have to be primed to interpret this. And so, I think also you can imagine it starts to get very, very complicated. So in the case of single numbers like climate sensitivity or global sea level rise or that likelihood of West Antarctic ice sheet collapse, there's a few things where actually Bayesian methods are used because it's a single number. And especially for climate sensitivity, there is sort of a narrative of the different storylines, if you like, of different climate sensitivity and what it would take to create high or low. And also, I think ice sheet collapse. But once you get to regional climate, I think there's too many variables, and it would just become crazy. But for a national climate assessment, it would be very, very possible. So I think actually, I'm not really arguing that IPCC should do something different. I think given the constraints that they're under, that's probably what they can do. But I must say, it does create a disconnect between work group 1 and work group 2, because work group 2 is looking at the impacts, and they do look quite specifically. You can't connect the work group 1 science to the work group 2 science. It's been a major problem. But I think it'll happen at the national, more at the national scale.
Jochen, yeah.
So just a much more technical question, I think. So these coastal networks, in what sense are they different from Markov chain?
Well, it is a Markov chain, I guess, isn't it? But it's not. There's no, except that I guess I've done them without necessarily a time sequence. So the ones this one. Ellen is.
It might be sometimes it might be one, sometimes not.
No, this one is. Yeah. So I think it very much connects, and actually you can have time series causal networks, and where I guess it really is just a Markov chain. Yeah. So I think the nice thing I think all the mathematical framework is there. Of course, you have to make choices. Like the weakness of this, as you say, she's divided, and so into 3 states, which is pretty typical, of course. That's probably not so much controversial, but then PGO1, and they're uneven, 2 states. So you have to make choices in how you bin things, and all those. So there's a lot of.
Given you've done that, I understand that this is.
No, but it's the same mathematics, yeah. So there's a lot of room to optimize some of these networks, I would think, as well.
Okay, thank you, Ted. Yeah, and we move on.